Welcome everyone. Today, we'll discuss anodic protection, an electrochemical method that plays a crucial role in preventing corrosion. This technique is especially important in industries dealing with aggressive chemical environments. Let's start with an overview. Anodic protection is a specialized corrosion control technique that maintains metal surfaces in a passive state using an external anodic current. This approach is particularly effective for metals that can form stable passive films. Anodic protection is an advanced corrosion control technique that involves maintaining a metal surface in its passive state by applying an external anodic current. This method is particularly effective for metals that exhibit passivity, such as stainless steel and carbon steel in certain environments. The importance of anodic protection lies in its ability to significantly reduce corrosion rates, extend equipment life, and minimize maintenance costs. Unlike cathodic protection, which is suitable for active metals, anodic protection is ideal for environments where metals can form a stable passive film, such as in strong acidic solutions. By controlling the electrode potential within a specific range, anodic protection ensures that the metal remains in a passive state, thereby preventing localized corrosion and pitting. This technique is widely used in industries where equipment is exposed to aggressive chemicals, making it a critical component of corrosion management strategies. Before diving deeper, we need to understand passivity, the phenomenon where metals form a thin oxide layer that acts as a protective barrier against corrosion. Passivity refers to the phenomenon where certain metals, when exposed to specific environments, form a thin, adherent oxide layer that significantly reduces their corrosion rate. This passive film acts as a barrier between the metal and the corrosive medium, preventing further attack. Metals such as stainless steel, titanium, and carbon steel in concentrated acids exhibit passivity under controlled conditions. The mechanism involves the formation of a stable oxide layer when the metal's potential is maintained within a narrow range known as the passive region. Outside this range, the metal may either corrode actively or undergo transpassive dissolution. Understanding passivity is essential for anodic protection because the technique relies on keeping the metal within this passive region using an external current. Factors such as temperature, solution composition, and impurities can influence the stability of the passive film, making precise control of potential critical for successful anodic protection. Now, let's look at the key components needed for an anodic protection system. An anodic protection system consists of several essential components that work together to maintain the metal in its passive state. The primary elements include a power supply capable of delivering controlled anodic current, a reference electrode to monitor the potential of the protected structure, and a control unit that adjusts the applied current based on feedback from the reference electrode. Additional components may include data acquisition systems for monitoring and recording performance, alarms for detecting deviations, and protective enclosures for harsh environments. The reference electrode, often made of materials like platinum or silver chloride, is critical for accurate potential measurement. The control system uses this data to ensure that the metal remains within the passive region, avoiding both active corrosion and transpassive breakdown. Proper selection and maintenance of these components are vital for the reliability and effectiveness of anodic protection systems. Designing an anodic protection system involves several critical considerations. Designing an anodic protection system requires careful consideration of several factors to ensure its effectiveness and safety. Key concerns include determining the correct potential range for passivity, selecting appropriate reference electrodes, and ensuring reliable control mechanisms. The system must be capable of responding to changes in process conditions such as temperature, concentration, and flow rate, which can affect the passive film stability. Safety is another critical aspect, as improper potential control can lead to transpassive corrosion or hydrogen evolution, causing equipment damage or hazardous conditions. Additionally, the design should account for redundancy in monitoring and control to prevent failures. Economic factors, such as initial installation costs and long-term maintenance, must also be evaluated. A well-designed anodic protection system balances technical performance, operational safety, and cost-effectiveness, making it a sophisticated solution for corrosion control in aggressive environments. Where is anodic protection used? Let's explore some industrial applications. Anodic protection is widely applied in industries where equipment is exposed to highly corrosive environments. Common applications include storage tanks and reactors for concentrated sulfuric acid, phosphoric acid, and acetic acid. It is also used in the chemical processing industry, where carbon steel vessels require protection against aggressive acids. The pulp and paper industry employs anodic protection for digesters operating under acidic conditions to prevent rapid corrosion of steel surfaces. Other sectors include food processing, pharmaceuticals, and wastewater treatment, where maintaining equipment integrity is critical for safety and efficiency. The technique offers significant advantages in reducing downtime, extending equipment life, and lowering maintenance costs. Its ability to provide long-term corrosion control in environments where other methods are ineffective makes anodic protection an indispensable solution for many industrial processes. Here's a real-world example from the pulp and paper industry. In the pulp and paper industry, digesters are exposed to acidic conditions that can cause severe corrosion of carbon steel. Anodic protection is implemented to maintain the digester walls in a passive state, significantly reducing corrosion rates. The system includes a power supply, reference electrodes installed inside the digester, and a control unit that adjusts the applied current based on real-time potential measurements. This approach has proven highly effective, extending the service life of digesters by decades and reducing the need for frequent repairs or replacements. The economic benefits are substantial, as downtime for maintenance is minimized, and the risk of catastrophic failure is greatly reduced. Additionally, anodic protection contributes to environmental sustainability by preventing leaks of hazardous chemicals. This practical example demonstrates how anodic protection can be a cost-effective and reliable solution for industries dealing with aggressive chemical environments. Sources and further reading. Key references for anodic protection include academic papers, industry standards, and technical manuals. Recommended sources are Corrosion Engineering, by Mars G. Fontana, NACE International Standards on Anodic Protection, and research articles from journals such as Corrosion Science and Journal of Electrochemical Society. These resources provide detailed insights into the principles, design, and applications of anodic protection systems. For practical implementation, case studies published by chemical and pulp industry associations offer valuable real-world data. Consulting these references ensures a comprehensive understanding of anodic protection and its role in modern corrosion control strategies.